Hey everyone, thanks for coming to my talk. My name is William Tran. I'm a principal software developer at Pivotal, and I'm here to talk about some ideas I have around microservice security that I hope you'll find useful. Feel free to take notes and snapshots on my slides, but you can find everything on my GitHub repo. The link is right there. And who of you attended the first talk this morning about JOT? Okay, good, some of you. I hope those that didn't raise their hands already know about JOT, and for those that learned something this morning, thank you, Nicholas. You're making my life a little bit easier. We're going to assume that you kind of know what JOT is all about. If not, hopefully you'll be able to pick it up. First, a bit about me. I've been a Spring user for a bit over a decade, since Spring 2.0. And it was actually my first job at a university where we were also one of the first customers of AWS. And 10 years later, and through many strokes of luck, I'm with the Spring team at Pivotal, where I've been able to contribute to Cloud Foundry's authorization server called UAA and the Spring Cloud project. And I'm currently working on Spring Cloud Services, which is a product that runs on Pivotal Cloud Foundry. And I'm based in Toronto, Canada. I want to begin with a few reminders of the nature of microservices. By now, I'm sure you've heard a lot about what microservices look like, but I'd like to highlight a few characteristics that are relevant to this talk. They're mostly HTTP-based, but there's times where invocation over a messaging backend makes sense, like via RabbitMQ or Kafka. They're independently deployable, or at least we strive for that, and we also strive to write microservices that have a single responsibility. Of course, they all run in their own separate processes. Multiple wars in a single app server does not count as microservices. It's also really important to highlight some characteristics of the organizations that deliver microservices compared to more traditional software delivery. We have more teams, smaller teams in fact. Some call them 2 pizza box sized teams. And we also have teams that are more independent, a lot like the services they deliver. We might have more trust boundaries as well, but why would there be a trust boundary when you're all working for the same company? And this might depend on the kind of organization you work for. One example of a trust boundary is where one team isn't allowed to deploy another team's services. Now, does that translate to the way services interact with one another? We'll explore that in a bit. And why are we going to all this trouble in the first place? This is the biggest reason, to go faster, but we need to do this securely. But that's not so easy. So to rip off Biggie, more processes, more problems. Let me show you what I mean by starting with the traditional OAuth2 authorization code flow, where the auth server, app, and resource are all part of the same organization in this particular example. We have a browser that's accessing an app that requires authentication. And the browser doesn't have an authenticated session yet, so the app redirects it to the auth server. And so the auth server makes the user authenticate, and after the user authenticates, the auth server redirects back to the app with an authorization code. And then the app gives the auth server this code, and in return gets a JOT signed by the auth server. The app stores this JOT in session, and the browser session is now authenticated. The app makes a request to a resource server with this JOT in the header, and then the resource server validates the JOT and responds with data. And the app can finally take this and render the page. Raise your hand if you get this flow, or if this is a familiar flow to you. Okay, good. Okay. All right, now let's see what happens when the resource server needs to make other downstream requests. The browser makes a request to another page, and the app uses the JOT stored in session to make another call to the resource server. And that resource server validates the JOT and relays it to other downstream services. So it's just relaying the same token. And these services continue to do the same thing. So what do we end up with? One token to rule them all. This can be dangerous because the token is too powerful. It can be used to do anything to any service that'll accept the token, which in our example is all of them. The only thing that limits this token's use is the token's expiry. So token leakage is a big deal. Even if servers that'll accept the token are behind a firewall, and not publicly accessible. Some threat that's made its way into your system can exploit it. And this makes internal fraud easy. So is there another standard OAuth2 grant type that we could use instead? The client credentials grant type is designed for service-to-service interactions, so let's try that. Let's start back from where the app makes a call to the resource server with a user's JOT that was stored in session. So the resource server takes the JOT from the app, validates it, and authenticates the request. And then it gets a new token from the auth server using the client credentials grant type. This is essentially just doing basic auth with the auth server. And in return, resource gets a token back that represents itself. Now the resource server can use its JOT downstream. When A and B receive requests from the resource server, they use the incoming JOT to authenticate the request. And by validating the JOT, they can see that the request is coming from resource. In the body of the request, resource says it's acting on behalf of the user. But this is not so good because downstream services are now vulnerable to a confused deputy attack. A confused deputy is a program that is fooled into misusing its authority. And this happens when one app fully trusts another by virtue of the app's identity alone. In our example, A and B fully trust resource, and because of this, resource can be a confused deputy. Because where's the proof that resource is acting faithfully on behalf of the user? How can A and B know if the user is actually authorized to perform those operations? All A and B got was just a JOT that said who the resource server was. So if resource is compromised, A and B will also be compromised, and this could allow an attack to affect the entire system. So let's think about what happens when trust is misused in the real world. If apps fully trust one another, do teams fully trust one another as well? And maybe transitively because of the way their apps behave, but doesn't that go against an organization's policy of only allowing teams to deploy their own apps and not other teams' apps? So we have a bit of a problem here where the organization's trust boundaries are not reflected in the system. So what happens when trust boundaries aren't respected or don't exist at all? Some examples of this could be not checking another person's work for correctness, like not having code reviews. Or maybe you give a single person the privileges to perform multiple critical tasks, like the ability to both commit code and push that to production. In other words, you have no separation of duties. Well, then you get cases of massive internal fraud. And maybe it's a bit of a stretch to connect a confused deputy attack to these examples of fraud, but they were caused by a lack of internal controls. And WorldCom is so defunct, I couldn't even find a high-res logo for that one. It just doesn't exist. So here's a scary number. 60% of all attackers are insiders. This is a number that IBM Security came up with in their 2016 Cybersecurity Intelligence Index. So because of this, you can't just rely on perimeter security. You need internal controls in your system. Don't let one bad apple spoil a whole bunch. So how can we limit the effect of a confused deputy? At a bare minimum, we need to authorize based on more than just the caller's identity. We need to take into account the user and the scope of their token as well. So what if we sent both the client and the user's token as separate values? So in this case, resource would take the user's JOT and then send its own JOT as well as like a separate value. Well, this isn't foolproof because the combination is not integrity protected. What you really need to do is authorize based on a composite token that combines the user and the client, rather than multiple token values that could be rearranged. And better yet, if you authorize based on a call stack, then you have no information loss, and you can specify the expected behaviors of the system with a high degree of precision. Well, there is a new proposal for an extension of OAuth2, and it's called Token Exchange. And the most current draft of this spec is at that link. Here's how it works. Let's go back to our example where the app makes a call to the resource server with the user's JOT that was stored in session. The resource server requests a new token from the auth server using the token exchange grant type. It's like the client credentials grant type, where the server identifies itself using its own credentials, but it also includes the user's JOT it received, as well as the intended recipients of the new token. So the token request expresses who the user is, who the caller is, and who the intended recipients are. The auth server authorizes this action and returns a token expressing this intent. The resource server then uses this token to make requests on A and B can verify the token and the intent it carries. So in a nutshell, token exchange involves providing the actor, the subject, and the audience to the authorization server and getting a new token. So I'm using the words actor, subject, and audience because those are the terms they use in the spec. And check out the spec. It's actually not too hard to read through. So in other words, the authorization server makes a policy decision based on the caller, the user, the intended recipients, and the operations to be performed on them. And if that's approved, then the authorization server issues a new token that expresses the caller, the user, and the intent. The spec also allows for nested actor claims. So given a token previously issued via token exchange, the authorization server can make a policy decision based on a delegation chain, or in other words, an entire call stack. And another way of looking at this policy decision is that it's based on aggregated trust, not just the trust established by a single party, which is a pretty interesting idea. And now we have a way to take into account internal trust boundaries, but with more trust boundaries, you have a different set of problems. First, there are clear advantages to the token exchange grant type over the standard ones. You can have the user, the client, and the call stack be part of a policy decision. And because you can exchange tokens for new ones without the user's involvement, you can request tokens with a very narrow audience and scope to limit its power. Your trust boundaries are unambiguous through nested actor claims and can be respected in authorization decisions. So in other words, authorization decisions don't need to assume anything about the sequence of events that led up to the decision because everything is right in front of the decision maker. Your authorization server can provide centralized policy management and enforcement. And if you can build all this into an authorization server, I'm pretty sure you'll have a product that people will pay for. But there are some disadvantages. Each authorization decision and token grant incurs network overhead, and the auth server also incurs that overhead, which can make the authorization server become bottleneck. This bottleneck can be alleviated, but then you're having to deal with a trade-off between security and performance. So for example, instead of getting a new token for every request, you could employ token caching and reuse through a longer token expiry, or through a less restrictive or more permissive token that contains more scopes or audiences. But then you've got tokens that are more powerful and have a higher abuse potential. Finally, depending on how you implement policy management, centralization of policy management can get in the way of agility. Because who knows best how the system is supposed to behave at the level of individual service interactions? The developers of those services or security operations. So you might be better off to give those that define the services a way of defining those policies. And the issues we need to deal with don't just stop at auth. Message security is also a concern. We need to protect the integrity and confidentiality of data in transit. HTTPS or TLS everywhere is a definite start. But here's an example of its limitations. Say we've got an online shopping app where shop plays the role of the user-facing app, cart is a resource server, and payments is downstream of that. The user enters the credit card info at the checkout screen and hits the confirm payment button. HTTPS provides confidentiality and integrity between the browser and shop. So shop passes the user input along to cart, which provides the actual checkout functionality. Again, this request has confidentiality and integrity. And cart calls payments to settle the order, passing along the credit card info. So here's the thing. Does cart really need to see the credit card info? Payments is the only service that actually uses it. HTTPS only gives us point-to-point confidentiality and integrity. Now, we could flatten things out so that payments can be directly called by shop. But this limits our architectural choices, and it could overcomplicate shop, because cart can't be a facade for checkout functionality anymore. So from this example, we can see that end-to-end security can't be solved at the network layer alone. This needs to be dealt with at the application layer. WS Security tried to solve this a decade ago for SOAP and XML, but it was way too complicated. And it still had its flaws, mostly over canonicalization, being able to trick parsers into doing weird things. Those flaws are still there. So here's what we really need to achieve. End-to-end message security to address that last example with the credit card info. And we need to stop assuming trust based solely on the caller's identity. We need to limit the effect of token leakage and misuse. And we need to break out of the performance versus security trade-off that occurs when the auth server becomes a bottleneck. So here's my take on a solution. But I need to warn you first. The solution is experimental, bleeding edge. Please don't run this in production. Look at the commit history. I've been working on it like just a few hours ago. But because I haven't seen anyone try this yet, I'd really like your feedback because this could be the start of something important. You can find the code on GitHub at pivotalcfexperimental/Spring Cloud Services Security. It's Apache 2 licensed. And the complete proof of concept will soon run on Pivotal Cloud Foundry using Spring Cloud Services config server and service registry, as well as Pivotal single sign-on as the authorization server. But I'm not here to do this product pitch. You'll also be able to check out the code and run all of it locally with configurations for open source Spring Cloud and UAA, Cloud Foundry's authorization server. And you should be able to plug it into really anything you want. You'll see soon. The solution is based on Jose, which is not just a Spanish name. JOSE, or Jose, stands for JSON Object Signing and Encryption. It's not just for JSON payloads either. You can use it for any arbitrary content. And it's actually a whole suite of RFCs that are proposed standards as of May 2015. The ones we're using directly are JSON Web Signature, JSON Web Encryption, and JSON Web Token. The implementation uses Nimbus, Jose, and JWT, which is also Apache 2. So shout out to that team because they really make using these standards easy. And you can find more information at that link. The way we're using Jose for message security is through public-private key pairs. Oops. Yes, there we go. And we're using RSA because that's not the only algorithm supported. You can find more info at that link. All parties have key pairs. The sender signs an outbound message with its private key. And this provides integrity and confidentiality. Integrity and non-repudiation, which together means you can ensure who the sender is and that the message wasn't forged or altered in transit. The sender can then encrypt a signed message with the public keys of its recipients. And this provides confidentiality to ensure only the intended recipients can decrypt the message. Multiple recipients are supported using the JSON serialization of JWE, but unfortunately this isn't supported yet in Nimbus, but it's on the roadmap. On the recipient's end, the recipient can decrypt an incoming message with his private key and then verify the integrity of the message and the identity of the sender with the sender's public key. So where do we get these key pairs from? Well, you can use a PKI. PKI can supply your service with a key pair and a certificate. PKI also stands for public key infrastructure. So you get a key pair and a certificate which has identity built in. You could use Let's Encrypt for this. There's also a project called Netflix Lemur. Or you might already have your own. But I'm proposing an option that might turn out to be simpler. How about service discovery? This is something you might already have or are considering. Service discovery decouples service identity from physical networking. So you can address other services by their logical name rather than where they've been deployed. And this enables changes to deployment at runtime and shields consumers from changes in deployment. So one use case for this would be rolling out a new version of an API. There's a few service registries out there like Netflix Eureka, Apache Zookeeper, and HashiCorp's console. But we'll use Eureka in the solution. In Eureka, services register with the registry on startup. They register with a service name and how it can be reached, like a host name or an IP and port. Other metadata can also be registered as well, like a version number to support smart routing decisions. Now, how does trust play into a service registry? Services need to use the registry in order to look up each other. And this means they need to have a high level of trust with the registry to trust the routing information it gets from it, because where to send a request is really important. The registry also needs to receive registration requests from services. So it needs to be able to trust the information it's getting from the registering service. To establish this trust, you need to have authentication and access control. So to do that, each service needs to get its own credentials so that registration requests can be authenticated. We also need to prevent services from being able to modify another service's registration records. On Spring Cloud Services, which integrates Spring Cloud into Pivotal Cloud Foundry, we've already taken care of this for you by building a security layer on top of Eureka, and the platform runs Eureka for you. But this idea will still work on other registries that have security built in, like Zookeeper and Consul. The registration request itself needs to contain a public key as well as routing information. So you can just generate a key pair at startup time, register it, and then keep the private key private. You don't need to get it from anywhere or send it out anywhere. So with the trusted registration of a public key, the service registry can be used to prove service identity. To wrap up this bit on service discovery, we can see that because it manages service identity and location, it needs to be trustworthy. If you can trust it, you can do some cool things with it, like use it as a lightweight PKI. So when you've got your PKI sorted out, you can use it to sign all of the things using JSON Web Signature. The sender uses its private key to create JWS payloads. And I'll just pause for a second. JWS, like you know about JWT, JWT is just a specific use case for JWS. JWS is pretty much the same thing if you understand JWT, but you've never heard of JWS before. So over HTTP, you can sign the request, the response, as well as the request and response headers. But you should just pick the ones that matter to you. If you're not using HTTP, no problem. JWS is general purpose, so you can use it in pretty much the same way. For example, in Spring Cloud Stream, which can help you build message-oriented microservices backed by RabbitMQ or Kafka, messages also have headers and bodies. So now on the receiving end, you can verify all the things. The receiver uses the service registry to map the sender of the message to its associated public key, and then uses the public key to verify the signature of the payload. Payloads are now traceable to the individual service that registered. You can also use key pairs to encrypt some of the things using JSON Web Encryption. To do this, the sender uses the service registry to look up the public key of the receiver. It then uses the public key to encrypt the payload. When using encryption, you should always sign the payload first before encrypting. If you don't, anyone with access to the receiver's public key can just encrypt its own message and spoof it. You can even encrypt a payload from multiple receivers, all each using different public keys. This is possible through the JSON serialization of JWE. You can also use JWE for entire message bodies or for just objects or fields within a message body. And you can just embed that into some plain text. But while message integrity and traceability are things that should be a baseline, confidentiality might not be required in all situations. So use it where it makes sense, like with that credit card info in the previous example. Now that we have the easy part out of the way, and I'm saying that facetiously, of course, we can move on to the hard stuff. But I'm saying easy because the Jose specs for message security have been made easy with libraries like Nimbus, Jose, and Jot. But you do need to understand the specs before you go off and use it. If you take a look at my repo, you'll find links to some great resources for understanding these specs. So are we there yet? Well, we covered end-to-end message confidentiality using JWE, and message integrity using JWS, which has service authentication built in. But we still need to deal with authorization. Ideally, we need to assert and authorize a call stack and stop assuming trust based solely on the caller's identity. We need to limit the effect of token leakage and misuse. And it'd be really great to be able to break out of the performance versus security trade-off that we get into using token exchange. So the solution I want to propose is to decentralize and embed all of the things. What do I mean by that? Let's start with self-issued JOTs. So instead of authentication based solely on JOTs coming from an authorization server, services can authenticate with each other using JOTs they create and sign themselves. JOT is just a specific use case of JWS. We're just defining the payload to be certain values that describe the invocation. Services can authenticate by verifying with the sender's public key, as in my previous description of JWS. And services can create as many JOTs as they need without network overhead. And if you can create as many JOTs as you need, you can have single-use JOTs that have a short expiry. And the JTI, which is random value used as the identifier for the JOT, can be used to prevent replay attacks entirely with the help of data store. Each single-use JOT can express the intent of an invocation in a precise and unambiguous way by expressing the intended recipient and the operation to be performed on it. In this way, the token has very limited power and can only be used for its intended purpose and only once. If you have your services only accept these JOTs and not the user's token, then the user's token has no power on its own. So then how do we present the user's token to downstream services and solve the confused deputy problem? Through nested self-issued JOTs. The incoming JOT can be nested inside another self-issued JOT for use downstream. So the call stack, starting with the user's JOT, can be expressed as nested JOTs, sort of like layers of an onion. With this, you get a verifiable chain of custody, which can also be thought of as an audit trail, showing that each party that's involved in the invocation. And the call stack can be verified by verifying each JOT recursively. And any attempts to break or forge this chain of custody can be detected. We get this property because the sender and intended receiver is encoded in each JOT. You just need to match these up when verifying the chain. These chains are finally wrapped in another JWS, which doesn't get propagated. It's like an envelope that you open up and throw away. And the chain inside, the chain is inside the envelope. The signer of the envelope has to be the same as the last signer in the chain for the chain to be valid. In this way, any attempt to reuse a truncated chain would be detected immediately. So here's the problem with using nested JOTs on their own. You can see in step 1, shop issues its JOT to cart, including the user's JOT that it negotiated from the authorization server. And then so cart takes that JOT and needs to make a call to payments in step 2. So cart takes that JOT from shop and wraps it in its own JOT, gives it to payments, payments authorizes it. Now payments is going to do something funny in step 3. Payments wants to just peel away one of those layers and reissue that JOT back to cart, kind of like a replay attack. And cart will actually just think that this is a valid JOT if it has no replay checking data store. So this is how we prevent chain truncation using a JWS envelope. So in step 1, shop issues a JOT wrapping the user's JOT, but then it wraps that JOT in an envelope. And then cart gets this, and it'll authenticate this package because it sees that the envelope and the JOT that's inside it are signed by the same person. And so cart will discard the shop envelope, wrap that with cart's JOT, and then wrap that in its envelope. So then in step 3, payments tries to peel away those layers. And then it wraps in its payments envelope, but that is going to be detected immediately because the signature of the envelope and the signature to the JOT does not match up, or the signing key is not the same. So here's an example of a nested JOT and how to verify the chain of custody with the service registry. We start off with our service registry here based on our online shopping example. Each row is an instance record. So for apps that are deployed across multiple instances, you'll see a row for each instance. But in this example, we just have one instance per app. An instance record has an ID, an app name, a location, and some metadata, including a public key. So let's say payments receives a token. And if this is really hard to read, then just look at the slides again and you'll be able to see it on your screen. It will make sense. Payments receives a token and it looks like that. And so let's start verifying this JOT. Looking at the issuer claim, it's 456. We can see that as instance ID 456 in the registry. And so we can get its public key from the metadata and use it to validate the JOT signature. Now that we have a valid JOT, we need to make sure that we are the intended recipient, that this is the actual operation to be performed. Just check that against the actual HTTP method and path. So you can see here that the op claim is post pay forwarder 1, 2, 3, 4, 5. So the token says this. Is this the actual stuff that I'm getting off the HTTP request? And if that's true, then continue. And now we better see that, we actually check the expiry as well. Check that the token isn't expired. There's the timestamp there. And now we need to see where this token came from. We can see that issuer 456 is instance ID 456, whose app name is cart. So we better see that cart was invoked with a token that was meant for it. So let's open up that token and validate its signature. The issuer is 123. So we can look that up in the service registry, get the public key, and we can validate it. Now we can line up we can validate the chain of custody. We can see that cart was invoked with a token that was meant for it in the odd claim. Let's see my laser pointer thingy. Okay, cool. So yes, we can see that cart was invoked with a token that was meant for it in the odd claim. And then cart generated its own token, this is the token generated by cart. And we can see the issuer here is 456, and that agrees with what's in the registry. This is cart. And then it uses this on payments, of course. This is, yeah. Okay, so now let's see where this token came from, the token that was received by cart. So this is issuer 123, and 123 is the app shop. And it included the user's token in the INI claim, which is used for the initial token. And we can open this token up and verify its signature. So the key for verifying this token can be downloaded from the authorization server, which is known and trusted by all services for issuing user tokens. Okay, but that's not enough just to express a chain of custody. We need to make policy decisions based on that. And here's how we can make that scale. Services need to make authorization decisions on their own. The policy they use to base those decisions on can be externalized as configuration, instead of being hard-coded into the services themselves. For those familiar with externalized configuration in Spring, this means using something like Spring Cloud Config Server. With this, we don't need to make any additional calls for authorization, which is a big win for performance. And policies can also be as stringent or as flexible as we want to allow services to evolve without needing to update policy each time. So here is an example of such a policy. This is a policy applied to payments that says when an incoming token has an operation claim matching post pay for order, then that token must have an initial token where the scope contains shop.customer. And this call stack has to look like cart, then shop. So this is kind of in reverse, so the most immediate callers first. So cart gets invoked by shop via operation post cart confirm. And I'm not married to this policy syntax. This is just some DSL I came up with, and And I'm looking for feedback, of course. We can make this better. So a nested token, like in this example, would comply with that policy. We can see the initial token here does have the scope shop.customer, and that the chain of custody started at shop and then went to cart via post cart confirm. We can take all of this even further by including custom claims in self-issued JOTs. And this lets services make their own claims about anything. And these claims will propagate and can be verified by any downstream app at any depth. One example could be the shop app, including a geolocation claim, which could be used by payments in some way. We can also have services generate custom assertions for fine-grained authorization. And this is just a matter of calling a service and getting a signed object back as a response. This object can then be given to another service as an assertion. With JWS, we've got the building blocks for any sort of custom authorization decision that doesn't need to rely on a central authorization server. All right, enough vaporware talk. Let's see it in action. In this demo, I want to demonstrate the core verifications that take place, like chain of custody verification, token expiry, and verifying token intent through the audience and operation claims. I'd also want to show you what invocation path policies can look like and how to make them as rigid or as flexible as you need. So here's the first demo that I want to show you. It's this chain of events that happens, and it doesn't have to be HTTP. It could be anything. Browser makes a call to shop. Shop calls cart with a checkout operation. Cart calls inventory to commit, and inventory calls suppliers to resupply. And so let's see some code. How's that? Okay. Okay, so this is the happy path. I'm going to run it. You can check out this code and run it as well as you wish. Okay, test passed. You can see some output in the console. And so I'll just walk you through what's going on here. Shop signs a message for cart. So we've got these little test apps, and it's really basic stuff here. I really wanted to show you some actual HTTP stuff happening, but this is as far as I got. So shop signs a message for cart, and this is the recipient, the intended recipient. That goes in the odd claim. This goes in the operation claim. Here's some message body. Hello, cart, time to check out. Cart receives and verifies this message. In the verification, we're telling it what the expected operation is. So this is going to be, let's say, the thing that you read off your HTTP request that says what the method and path was. So when that happens, then we can see some console output. Cart got the message body. Hello, cart, time to check out. So we can also see here that I'm just sending a string in the as a JWS body. And it could be some binary stuff, whatever you want. So then cart signs a message for inventory, including the token chain it got from shop. So this sign message call has an extra parameter here, verified message.get token chain. So this token chain here, this is the thing that actually shop created. Shop creates a message. Cart verifies the message, and then this is the verified token chain. So it's taking the token chain that got from shop and including it into this message that's going to inventory. And so inventory receives and verifies this message, et cetera, et cetera. So you can sort of see this chain of events here. Let's take a look at what this actual token is. Okay, I hope I have jot.io open. Yes, okay. So I'm going to rerun this in debug. Okay, so the verified message, I'll take the signed message here. So this signed message, this is what, in the last step here, suppliers gets this signed message from inventory. So it's the last step in this process. And we can look at the body of the signed message. So this should be the message body. And so what you're looking at here is a JWS. We've got a content type here of text plain. So you can just apply this text plain to this base64 data and parse it out however you need to. You can also see in this header here, there's a JTI claim of 650, And so this can be used to link the token to the body. So that token and body are inseparable. You can't like break it apart. And so that's the payload. Hello suppliers, time to order new goods. Okay, so this token chain envelope here, this is what actually gets transmitted in the headers. So this comprises of our token. And what is this? This is the envelope that we're looking at. So this is still a JWS. Here's the header. The content type is a jot. So what's inside is an actual jot. Let's take this payload. And how many of you have used jot.io as like a jot debugger? It's pretty useful stuff. Okay, good. So you know what I'm doing here. Okay, so I took that payload and put it into that window. And so now we're actually looking at the jot here. We can see that this jot is meant for the supplier's application, and it's meant to trigger the resupply operation. And then there's this jot claim here. This is the that nested jot. And the body is true. Oh, and look at the JTI. The JTI here is 6503. This is the same JTI that was used in the body. So this token is linked to the body. Okay, and so we peel away a layer, and we can see that the inner token here was a token for inventory to call commit on it. And peel away another layer. And so we can see that inner token was meant for cart to call checkout on it. And then the recursion ends here because there's no JWT claim. There's an INI claim. This is the initial user's token. And I'm actually just using an opaque value. So the initial user's token doesn't have to be a jot. And then it's up to you just to plug in your own resolver for resolving this value to some the user's claims. Okay, that was the first demo. All right, second demo here. Is a broken chain of custody. So what's going on here is shop gets a request, shop makes a request to cart makes a request to inventory makes a request to suppliers. But it's going to try to do something funny. It's going to try to take the token chain in the state that it was in when shop makes a call to cart. So it's going to peel a layer away from that token and then reuse it on suppliers. Not really reuse it on suppliers because suppliers hasn't out seen this token yet, but it's going to use a token with the chain of custody that's broken. So you can take a look at this test here. read through those comments. The only thing that's different here is that we're saving, this should be token chain from shop. Oops. That looks better. Okay. So shop signs a message, cart verifies that message. We're going to store the token chain in this variable here. Inventory is going to use that token chain, and that's proper. Inventory can take that token chain and send it to, or cart can take that token chain and send it to inventory. And then inventory, what inventory is going to do is going to take that token chain from shop. So not the token chain it received, but one layer peeled away. And it's going to try to execute that on suppliers. So let's see what happens. And well, the test passes, but we expected this verification exception. And here's the exception. Chain of custody is inconsistent at depth 0. Token issued by odd value inventory, but parent's token's odd was cart. Okay. So yeah, you can't really mess around here. Last example I want to show is supporting two different paths. So shop can call cart with checkout. Cart can resupply. Cart can call resupply on suppliers directly, or inventory can do the same thing. How much time do I have left? 5 minutes. Oh, perfect. Thanks for the sign. Okay, we're almost done here. Okay, so this test fails because the policies do not match the invocation. And so we can look at the policy over here. So suppliers needs to accept a request to resupply from both cart and inventory. So to do this, we can just add optional. And so what I'm using here is STS's Spring Tool Suite, its ability to do auto completion to add configuration properties files. And so this DSL syntax is defined as configuration properties. Okay, so we can make the inventory call optional, and the call from cart. Cart can call both commit and resupply, so we're going to change this to a one of okay. So in showing you this optional bit here, you can make policies a little more flexible to account for things like upcoming changes or migrations to your architecture. Okay, test passes. Right. Okay, so let's get back to the presentation. Okay. No, I want you there. Great. Okay, so if you really use your imagination, you could have seen separate applications, each with their own policies, securely messaging one another and using a service registry for key distribution. But if your imagination didn't take you there, don't worry, these examples are going to get a lot better with all these features here, lots of integration with Spring. And I'd really like to add encryption, but we need Java library support for the JWE serialization. So I'd like to work on getting this supported in Nimbus. .NET needs it too, but Node.js already has all the features we need. So if someone wants to write an implementation for this in Node, go for it. And dealing with HTTP was my first goal, but non-HTTP was also important. So PubSub coming soon. Watch this space, watch for changes, send me feedback. This definitely won't take off if I get no feedback. And definitely stay in touch as well. Thanks for coming to my talk.